Right now, without moving a single muscle, you're hurtling through space at over 600 meters per second. Earth is spinning, orbiting, and at the same time being pulled by something enormous, something we cannot fully see, something dragging us through the universe for billions of years. In this video, we chase that force. We will find the invisible monster behind our galaxy, discover a void that pushes entire galaxy clusters, and uncover data that is forcing scientists to rewrite the rules of cosmic motion. If you enjoy this journey, hit like and subscribe. It genuinely helps us keep going deeper. Take a breath. We launch now. Close your eyes for 5 seconds. Go ahead. Count them. When you open them, you had already traveled over 3,000 m through space. You didn't feel it. Nothing shook. Nothing flickered. But you moved faster than any aircraft ever built. Faster than any bullet ever fired. Faster than almost anything humanity has ever created. We grow up learning that Earth orbits our star. That feels like the whole story. A planet, a star, a neat circular path every 365 days. Clean, simple, done. But that picture is missing almost everything. Earth is spinning on its own axis at around 1,000 miles per hour at the equator. That spin is what gives us day and night. But at the same time, Earth is also racing around our star at roughly 67,000 miles per hour. That orbital speed is what gives us seasons and years. Two different motions layered on top of each other, happening all at once. And that is still only part of it. Our star is also moving. The entire solar system, every planet, every moon, every comet, every speck of dust is orbiting the center of our galaxy at over 500,000 miles per hour. Picture a carousel at a fairground. The children on the horses are spinning in their seats. The horses are going around the carousel, and the fairground itself is moving down the road on the back of a truck. That is roughly what is happening to us. Spin inside, orbit inside, a greater orbit all at once, all the time. But even that is not the end. Our galaxy, the Milky Way, is also moving through space. Not gently drifting, racing, surging, being pulled by forces so vast they bend our understanding of distance and scale. Here is where the story gets strange. When scientists first started mapping the motions of galaxies in the 1970s, they expected the universe to behave in a relatively orderly way. Galaxies should be expanding away from each other, carried outward by the growth of space itself since the beginning of everything. Predictable, mathematical, calm. What they found instead was chaos. Some galaxies were moving in directions they had no business moving. Entire clusters were veering off course. Our own neighborhood of galaxies was drifting toward a single point in the sky at speeds that had no obvious explanation. Something was pulling them. Something was pulling us. Scientists at the time couldn't see it. They couldn't name it. They could only measure its gravitational fingerprint on everything around it. The way you might feel the pull of a whirlpool before you ever see the water swirling, the numbers pointed in one direction. Something enormous was sitting out there, hidden behind the thick plane of our own galaxy, drawing hundreds of galaxies, including ours, toward it at over 1 million miles per hour. They would eventually give it a name that sounds almost like something from an old horror story, the Great Attractor. But before we get there, we need to understand just how invisible it truly is. Because the reason we couldn't see it for so long is one of the strangest ironies in all of science. Our own galaxy was hiding it from us. And what scientists eventually uncovered when they finally looked behind the curtain was nothing like what they expected. For most of human history, the sky looked still. Stars rose and set with such precision that ancient civilizations used them as clocks and calendars. The heavens seemed eternal, unchanging, ordered. The idea that the entire Milky Way could be hurtling through space would have sounded absurd to anyone looking up from a field 2,000 years ago. It still sounds strange today, but here is the confirmed science. Our galaxy is moving through the universe at roughly 1,300,000 miles per hour relative to the ancient light left over from the birth of the universe. Scientists call this the cosmic microwave background. It is essentially the faint afterglow of creation spread across the entire sky. And when we measure our motion against it, the numbers are staggering. We're not drifting. We are charging. Now, the obvious question is toward what? In the late 1970s, a group of astronomers studying the movements of nearby galaxies noticed something they couldn't explain. Galaxies in our region of the universe were not simply riding the expansion of space outward in all directions. They were veering, clustering their motion toward a single region of the sky, as if something enormous, something with the gravitational grip of tens of thousands of galaxies, was pulling them all in. This phenomenon got a technical name, peculiar velocity. It means a galaxy's movement above and beyond what the ordinary expansion of space would predict. A galaxy with no peculiar velocity is just going with the flow. A galaxy with high peculiar velocity is being yanked somewhere specific. Our galaxy had a very high peculiar velocity. So did our neighbors. So did hundreds of galaxies around us, all pointing toward the same spot. An astronomer named Alan Dressler led a team that studied nearly 400 giant elliptical galaxies across our cosmic neighborhood. Their data confirmed it. The pull was real, consistent, and massive. Dressler estimated the source had the gravitational weight of tens of thousands of times the mass of our entire galaxy. He called it the Great Attractor, and the name stuck. But here's where it gets deeply strange. When scientists try to look directly at the spot where the Great Attractor should be, they hit a wall. A literal wall of stars and gas and cosmic dust billions of light years thick. The dense central plane of our own galaxy stretches across the sky like a glowing river. And directly behind it, hidden in what astronomers now call the zone of avoidance, sat whatever was pulling us. Imagine trying to find a fire behind a mountain range. By only watching which way the smoke drifts, you can measure the pull. You can calculate the mass, but actually seeing the source impossible with the tools they had at the time. So for years, the Great Attractor was a ghost confirmed by math invisible to every telescope. Scientists didn't even know if it was a single object, a cluster, or something stranger entirely. The model suggested it had to be there. The gravity was undeniable. But the identity of the thing dragging our galaxy through space remained a mystery. Then they found a way to look through the fog, using radio waves and infrared light, which can slip through cosmic dust in ways that visible light cannot. They began to peer behind the curtain of our own galaxy. And what they found there started to rewrite the entire map of our cosmic neighborhood. Because the Great Attractor was not quite what anyone expected, and what lay behind it was even less expected. There's a band of sky that astronomers have historically tried to avoid. Not because it is uninteresting, because it is almost impossible to see through. The Milky Way, our home galaxy, is shaped like a flat disk with a dense bright bulge at its center. When we look out along the plane of that disk, we are staring through hundreds of billions of stars, clouds of gas, and thick curtains of interstellar dust. The light from anything behind that plane gets scattered, absorbed, and warped beyond recognition. Astronomers named this region the zone of avoidance. It blocks roughly 20% of the entire sky from clear observation. And by extraordinary cosmic coincidence, the Great Attractor sits almost perfectly centered within it. It is as if you're trying to track a thunderstorm on the other side of a mountain range using only the direction the wind blows on your face. For decades, entire galaxies hid in this zone. The instruments simply could not cut through the interference. The galaxies were there. We just had no way to see them. Optical telescopes, the kind that capture visible light, are nearly useless in this region. The dust eats the light before it ever reaches us. The breakthrough came when scientists switched strategies. Infrared light has a longer wavelength than visible light. It passes through dust more easily, the way a foghorn carries through mist when a whistle cannot. Starting in the 1990s, teams of astronomers began scanning the zone of avoidance using infrared cameras, patiently building up a picture of what lay behind the curtain. They found galaxies, hundreds of them, thousands, entire clusters of galaxies that had simply never been seen before, hiding in plain sight behind the bulk of our own. One team, led by astronomer René Kron-Korteweg, conducted a particularly deep survey using a large radio telescope in Australia. Radio waves pass through galactic dust even more effectively than infrared light, and the survey detected the characteristic radio signature of hydrogen gas inside galaxies, allowing the team to identify and measure objects deep inside the zone of avoidance. But even as the Norma cluster came into focus, the measurement problem remained. The cluster was there. It was massive, but the revised mass estimates using the new data were lower than the original predictions. The Norma cluster alone wasn't nearly heavy enough to account for the full strength of the pull. Something else had to be contributing. A revised survey using X-ray observations and more powerful infrared data eventually produced a stunning result. The Great Attractor, the thing that had seemed so terrifyingly massive in early estimates, turned out to be only about 1/10 the size scientists originally believed. The first estimates had been wildly off. That sounds like good news. Smaller means less threatening, but it opened a far bigger problem. If the Norma cluster and everything around it wasn't massive enough to explain the motion of our galaxy and hundreds of others, then something else was doing the heavy lifting. Something farther away, something even larger. Scientists started looking deeper, past the zone of avoidance, past the Great Attractor itself, and in the direction our galaxy was ultimately heading. Several 100 million light years further out, they found it. A structure so vast that the Great Attractor barely registers as a footnote beside it, and it had been hiding in plain sight all along. Imagine finding out that the mountain you thought was pulling the river toward it is actually just a hill, and that behind the hill is an entire mountain range you had never seen. That is roughly what happened when astronomers looked past the Great Attractor, several 100 million light years beyond our galaxy. In the same general direction that everything in our cosmic neighborhood has been streaming toward sits one of the most massive structures ever identified in the observable universe. It is called the Shapley supercluster, named after the astronomer Harlow Shapley, who first noticed an unusual concentration of galaxies in that region nearly a century ago. At the time, Shapley had no idea what he was looking at. The tools didn't exist to measure it properly, but his notes recorded a strange excess of galaxies in one patch of sky, more than probability alone could explain. Modern surveys confirmed what he sensed. The Shapley supercluster contains dozens of galaxy clusters, each cluster holding hundreds to thousands of individual galaxies. In total, the structure packs the equivalent of roughly 10 million billion times the mass of our star into a region spanning several 100 million light years across. The numbers are so large they lose meaning unless you anchor them in something physical. So try this. If the Milky Way were a single grain of sand, the Shapley supercluster would be roughly the size of a large football stadium filled from floor to ceiling. And it is pulling on us, not gently, not distantly. Scientists confirmed that the Shapley supercluster contributes a significant portion of the peculiar velocity our galaxy has been accumulating for billions of years. It has been one of the primary engines behind our motion through space all along, quietly doing its work from a distance so vast that earlier instruments couldn't even register it. When scientists factored Shapley into their models of cosmic flow, the numbers began to make more sense. The missing gravitational force that the Norma cluster alone couldn't supply. Much of it was coming from Shapley, reaching across hundreds of millions of light years to tug on our galaxy the way the moon tugs on the oceans. But here is where the story twists again. Even after accounting for Shapley, the models were still slightly off. The motion of galaxies in our region of space still didn't perfectly match what gravity from all known structures could predict. Something else was contributing. And in a discovery that genuinely surprised the scientific community, researchers identified a force coming from the opposite direction. A push on the far side of our galaxy from the Shapley supercluster. Astronomers found a massive region of space that is nearly empty. Fewer galaxies, less matter, a cosmic void of extraordinary size. And because this void contains so much less mass than the regions around it, it generates something like an anti-gravity effect on its neighbors. Regions of high density pull things toward them. Regions of very low density effectively push things away. This structure was named the dipole repeller. It is not pulling us anywhere. It is pushing us from behind, shoving our galaxy toward the Great Attractor and the Shapley supercluster from the opposite direction. We're not just being attracted. We're being squeezed through space by forces on both sides simultaneously. Our galaxy is moving through a corridor of gravity and emptiness, pressed forward by a void and drawn ahead by an unimaginable mountain of mass. And the corridor itself is part of something even larger, something with a name that took decades to earn. In 2014, a team of scientists published a paper that quietly redrew the map of where we live in the universe. Using a new method to trace the flow of galaxies through space, following the streams of peculiar velocity, the way a hydrologist follows rivers back to their source, they identified a supercluster so vast that every galaxy flowing toward the Great Attractor could be considered part of it. A single gravitationally defined region of space containing over 100,000 galaxies, including our own Milky Way. They gave it a name from the Hawaiian language, Laniakea. It means immeasurable heaven. Laniakea stretches roughly 500 million light-years across. To put that in terms of something imaginable, if you shrank the entire observable universe down to the size of the continental United States, Laniakea would be roughly the size of the state of Texas. Inside Laniakea, galaxies are not scattered randomly. They flow. They stream along invisible threads and filaments of matter, all converging toward a central point. That central point sits in the region of the Great Attractor. All of Laniakea is in a sense slowly falling toward its own heart. For the first time, we had a name for our cosmic address. Not just the Milky Way, not just the local group of nearby galaxies, not just the Virgo supercluster, which had been our previous best answer. We live in Laniakea, a supercluster so large that it took the entire history of modern astronomy to identify. But Laniakea came with an uncomfortable truth attached. It is not gravitationally bound. That is a technical phrase with a deeply unsettling meaning. A gravitationally bound structure is one where the internal gravity is strong enough to hold everything together against the expansion of space. Galaxy clusters are gravitationally bound. Even some small superclusters are. Laniakea is too large and too spread out. The expansion of the universe is slowly winning the tug of war. Laniakea will not stay together forever. Over billions of years, the expansion of space will pull its outer galaxies away from the center, unraveling the supercluster thread by thread. Our galaxy will eventually be torn from the broader structure, left orbiting only its closest gravitational companions, while the rest of Laniakea drifts apart into the dark. Confirmed measurements of how space expands and how much mass Laniakea contains make this outcome essentially certain. We're living inside a structure that is already beginning to come apart at the edges. And the force doing the unraveling is the same force that has scientists puzzled right now. Because in the last few years, data from a massive New Sky survey has revealed something alarming about dark energy, the mysterious force behind the expansion of space. It may be changing. Dark energy was always assumed to be constant, a fixed background pressure built into the fabric of space itself, steady and unchanging across all of cosmic time. That assumption was the foundation of decades of calculations, models, and predictions. But the newest data covering over 14 million galaxies and particles of ancient light, called quasars, suggests the force driving expansion may not be constant at all. It may be growing or shifting or behaving in ways that our current models simply cannot explain. If dark energy is changing, the future of Laniakea and everything inside it, including Earth, may look very different from what scientists predicted. The map we thought we had of our own fate is being redrawn, and what lies ahead is stranger than anyone expected. For years, scientists had a problem without a name. They had the measurements. They had the direction. They had the gravitational fingerprint of something colossal, bending the paths of hundreds of galaxies. But a force without a face is hard to talk about, hard to fund research around, and almost impossible to explain to the public. Then came the Seven Samurai. That was the unofficial nickname for a team of 7 astronomers who, in the mid-1980s, embarked on one of the most ambitious galaxy surveys ever attempted at the time. Their goal was to map the motion of nearly 400 giant elliptical galaxies spread across our cosmic neighborhood, measuring how fast each one was moving relative to what the standard expansion of space would predict. It was painstaking work. Each galaxy required careful observation, careful measurement of its brightness and size, and careful calculation of its distance. Then the team would compare the actual position of the galaxy to where it should be. If nothing unusual was happening, the results were unmistakable. Galaxy after galaxy was off course. Not randomly, not scattered in every direction, the way you would expect if the discrepancies were just measurement errors. They were all veering toward a single region of the sky, a region sitting almost perfectly behind the obscuring plane of our own galaxy. The team calculated that whatever sat at that point had a mass roughly equivalent to tens of thousands of galaxies the size of the Milky Way. An extraordinary, almost incomprehensible concentration of matter. Astronomer Alan Dressler, one of the 7, gave this source its name. He called it the Great Attractor. The name was partly scientific, partly theatrical. Attractor is a term from physics describing a point toward which a system naturally evolves. Great was simply accurate. There was nothing modest about the scale of what they had found. When the findings were published, the scientific community reacted with a mix of excitement and skepticism. The claim was bold. A gravitational structure massive enough to pull our entire galaxy off course, hiding directly behind the one part of the sky that was hardest to study. It sounded almost too convenient, but the data held up. Follow-up surveys confirmed the motion. Different teams, using different methods, arrived at the same conclusion. Something enormous was there pulling on us with a force that had been acting on our galaxy for billions of years without anyone on Earth noticing. Think about that for a moment. For the entire span of human civilization, every empire, every war, every scientific revolution, every telescope ever pointed at the sky, Earth was being dragged through space toward this thing. And nobody knew. The force was too slow on human timescales to detect without modern instruments. The direction was hidden behind our own galaxy. The scale was too vast for earlier technology to resolve. It took radio, telescopes, infrared cameras, and supercomputers running models of galactic flow just to see the edges of it. And even after it was named, even after the papers were published and the conferences held, the Great Attractor remained stubbornly mysterious. Because all the early estimates of its mass, the numbers that made it sound so terrifying, were about to be dramatically revised downward. The monster was real, but it was smaller than anyone thought, which meant something else. Something even larger. Had to be doing most of the pulling. The Great Attractor was not the answer. It was just the first clue. There is no scale in the universe large enough to weigh a supercluster. You cannot send a probe to measure it. You cannot collect a sample. You cannot even see most of it directly. And yet, scientists can calculate the mass of structures like the Great Attractor with remarkable precision. The method they use is one of the most elegant in all of astronomy, and it depends entirely on motion. Here is the core idea. Gravity makes things move. The more massive an object, the more it bends the paths of everything around it. So if you can measure how much the paths of surrounding galaxies have been bent, how much their velocities deviate from what pure cosmic expansion would predict, you can work backward and calculate what kind of mass is responsible. Scientists call these deviations peculiar velocities. Every galaxy has 2 components to its motion. One is the smooth expansion of space itself, carrying everything outward at a rate described by the Hubble constant. The other is the peculiar velocity, the additional push or pull from local gravity. Measure the peculiar velocity of enough galaxies in a region, and you can map the underlying mass distribution, including the parts you cannot see. For the Great Attractor, teams of astronomers spent years cataloging the motions of hundreds of galaxies. They measured redshifts, the stretching of light as galaxies move away, and compared them against distance estimates calculated by other means. The gaps between expected motion and observed motion revealed the gravitational landscape in extraordinary detail. Early calculations in the 1980s suggested the Great Attractor had a mass tens of thousands of times greater than the Milky Way. It was a number so large it dominated all discussion of the topic for years. Then better instruments arrived. X-ray satellites could detect the hot gas trapped in galaxy clusters, giving a more direct measure of cluster mass. Infrared sky surveys could penetrate the zone of avoidance and actually count galaxies that had been hidden before. And as more data came in, the picture shifted. The revised mass estimates were much lower than the originals. The Great Attractor region, centered on the Norma cluster, contained significant mass, but only about 1/10 of what early models assumed. The early numbers have been inflated by incomplete data and by the difficulty of seeing through the galactic plane. This created a genuine scientific puzzle. If the Great Attractor was 10 times smaller than thought, what was supplying the gravitational force that was clearly moving our galaxy and its neighbors? The answer came from looking farther, much farther. Surveys that extended several 100 million light years out into space in the same direction of motion revealed an even larger concentration of galaxies. The Shapley supercluster, whose gravitational reach extended all the way back to our neighborhood. It was like realizing the wind in your face is coming from a mountain range 100 miles beyond the hill you were watching. The method of weighing by motion had worked perfectly. It had correctly identified that something enormous was pulling our galaxy. The only error was in assuming the source was nearby. The real driver was farther, older, and larger than anyone had initially suspected. And the same technique applied to newer data from deeper sky surveys has recently uncovered hints of structures even beyond the Shapley supercluster that may be contributing to our motion. Every time scientists extend the map, they find the pull goes deeper than they thought. The universe keeps revealing new layers of influence, and each one raises the same question. How far does it go? The zone of avoidance had kept its secrets for most of the 20th century. Optical telescopes, the kind that collect visible light, were essentially blind to anything hiding behind the dense plane of our galaxy. The dust and gas absorbed the light before it ever reached the detector. Entire galaxy clusters could sit right there, massive and ancient, and astronomers would see nothing but a smear of Milky Way haze. The solution came from switching to a different kind of light entirely. Infrared radiation has a longer wavelength than visible light. It behaves differently when it encounters dust. Where visible light is absorbed and scattered, infrared slips through, not perfectly, not without some distortion, but enough to make hidden objects detectable. Starting in the early 1990s, astronomers began systematic infrared surveys of the zone of avoidance, scanning strip by strip across the sky, building a catalog of everything that emerged from the obscuration. The results were striking. Galaxies appeared where none had been recorded before. Hundreds of them, then thousands. Entire clusters emerged from behind the curtain, like cities appearing out of morning fog. The universe behind our own galaxy was not empty. It was packed. One team, led by astronomer René Kron-Kortweg, conducted a particularly deep survey using a large radio telescope in Australia. Radio waves pass through galactic dust even more effectively than infrared light, and the survey detected the characteristic radio signature of hydrogen gas inside galaxies, allowing the team to identify and measure objects deep inside the zone of avoidance. Over the course of years, they cataloged hundreds of previously unknown galaxies, including several that clustered near the heart of the Great Attractor region. What had been a gravitational mystery with no visible source began to resolve into a real, identifiable structure. The Norma cluster sat at the center, surrounded by streams of galaxies feeding into it along cosmic filaments. It looked every bit like the heart of a major gravitational basin. Scientists confirmed that the motions of nearby galaxies were consistent with being drawn toward this structure. But even as the Norma cluster came into focus, the measurement problem remained. The cluster was there. It was massive, but the revised mass estimates using the new data were lower than the original predictions. The Norma cluster alone wasn't nearly heavy enough to account for the full strength of the pull. Slowly, painstakingly, the hidden landscape of our cosmic neighborhood came into view, and it was magnificent. A vast network of galaxy clusters connected by filaments of matter, forming a web-like structure that stretched across hundreds of millions of light years. Our galaxy sat within this web, being drawn gently, but irresistibly toward its densest regions. What had been an absence on the map became one of the richest cosmic landscapes ever charted. The zone of avoidance had hidden one of the most dramatic gravitational landscapes in the known universe for most of human history. But what the infrared and radio surveys also revealed, almost as a side effect of all this searching, was something even more unexpected. The cosmic web they were mapping was not just local. It extended outward in every direction, connecting our neighborhood to superclusters far beyond anything previously imagined. And threading through the entire structure, invisible but essential, was a form of matter that nobody has ever directly detected. Something that built the scaffolding long before the first stars ever ignited. And understanding it changes everything about how the Great Attractor formed in the first place. For 100 galaxies, all moving wrong. That was the data set that changed everything. When the Seven Samurai published their analysis of nearly 400 giant elliptical galaxies in the late 1980s, the most remarkable thing was not any single measurement. It was the pattern. Every galaxy in the sample that sat within a broad region of the sky was showing peculiar velocity, motion above and beyond what cosmic expansion alone would produce. And every one of those deviations pointed in the same direction. The chances of that being random noise were essentially zero. Something was pulling all of them. Something with enough gravitational reach to influence galaxies spread across a volume of space hundreds of millions of light years wide. The force was not coming from one spot. It was coming from an entire region, a broad gravitational basin toward which all the surrounding material was slowly flowing. To understand how extraordinary this is, think about what a galaxy is. A galaxy is not a small object. The Milky Way contains something like 200 to 400 billion stars. It stretches roughly 100,000 light years across. It has been forming stars for nearly as long as the universe has existed. A galaxy is in most human contexts the largest thing there is. And yet 400 of them were being moved off course by a single gravitational region. Follow-up studies expanded the data set dramatically. As survey technology improved through the 1990s and 2000s, astronomers added thousands more galaxies to the peculiar velocity maps. The pattern held. In fact, it deepened. The flow of galaxies toward the Great Attractor region was not the only large-scale motion detectable. Astronomers began identifying what they called bulk flow, a coherent drift of huge volumes of the universe in specific directions. Our region of space is part of a bulk flow that extends for several 100 million light years. Every galaxy within that volume, including every star within every galaxy, including every planet around every star, is participating in this drift. The flow is slow by everyday standards, but relentless by cosmic ones. Over billions of years, it adds up to enormous displacement. Confirming this required cross-referencing multiple independent data sets, peculiar velocity surveys, X-ray maps of galaxy clusters, infrared sky surveys, radio observations. Each method carried its own systematic errors and biases. But when scientists compared results across all of them, the bulk flow signal was consistent, real, reproducible. The universe was confirming from multiple independent angles that we live inside a gravitational current. One of the most striking visual representations of this came when researchers made animated maps of the cosmic flow field, essentially arrows showing which direction and how fast everything in a large region of space is moving. The arrows all converged. Not perfectly, not uniformly, but unmistakably, they pointed toward the same broad region, toward the Great Attractor, toward the Norma cluster, toward the Shapley supercluster behind it. The motion of 400 galaxies had been the first clue. The broader picture built from tens of thousands of galaxy measurements over decades painted something even more dramatic. We are not unique in being pulled. Everything around us, for hundreds of millions of light years in every direction, is being pulled too. We are all part of the same cosmic current, flowing together toward the same destination. A destination that, as it turns out, we will never actually reach. The reason why is one of the most mind-bending facts in all of modern cosmology. There is more to the universe than meets the eye. Much more. Everything you have ever seen, every star, every planet, every cloud of gas, every galaxy imaged by every telescope ever built makes up roughly 5% of the total matter and energy in the universe. The remaining 95% is something else entirely. Something that does not emit light, does not absorb light, and does not interact with anything in the way ordinary matter does. Scientists call roughly 27% of this invisible content dark matter. And without it, the Great Attractor and everything we have been discussing simply would not exist. Here's why. When the universe was young, very young, a fraction of a second old, the distribution of matter was almost perfectly uniform. Almost, but not quite. Tiny fluctuations existed, regions where the density of matter was slightly higher than average and regions where it was slightly lower. These fluctuations were extraordinarily small. But gravity is patient. Over hundreds of millions of years, the slightly denser regions attracted more matter. As they grew denser, their gravitational pull increased, attracting still more matter. The process compounded. The small fluctuations of the early universe grew into the first galaxies, then galaxy clusters, then superclusters. Dark matter accelerated every step of this process. Because dark matter only interacts through gravity, not through light, not through heat, not through any electromagnetic force. It could begin clumping together even before ordinary matter could. It formed the invisible scaffolding of the universe first. Then ordinary matter fell into the gravitational wells that dark matter had already created. The Great Attractor is not just a concentration of galaxies and hot gas. It is primarily a concentration of dark matter. The galaxies we can detect are sitting inside an enormous dark matter halo. The way foam sits on the surface of deep water. The foam is what you see. The depth below is what actually controls the dynamics. Remove dark matter from the models, and the math breaks immediately. Galaxy clusters would not hold together. The ordinary matter inside them moves too fast for the visible mass alone to keep it gravitationally bound. Galaxies themselves would fly apart. The large-scale structure of the universe, the cosmic web of filaments and voids that gives everything its shape, would never have formed in the time available since the beginning of everything. And here's the thing that should make you pause. Despite decades of searching, deep underground detectors designed to catch dark matter particles, particle colliders smashing atoms together at enormous energies, space telescopes scanning for any indirect signature, nobody has ever directly detected a single dark matter particle. This is confirmed. Dark matter exists. The gravitational evidence is overwhelming and comes from dozens of independent sources. But its nature, what it actually is, what it is made of, remains one of the great open questions in physics. We live inside a universe whose dominant form of matter is completely unknown to us. The structure pulling our galaxy across space is built from something we cannot see, cannot touch, and cannot name with any certainty. That is the confirmed state of our knowledge in the present day. And it gets stranger because dark matter is not the only invisible force shaping our fate. There is another component of the universe's hidden content that is doing something even more dramatic. Something that is actively working against the Great Attractor right now, at this very moment. And recent measurements suggest it may be changing in ways that rewrite the future. Deep inside the zone of avoidance, hidden for most of the 20th century, behind a thick curtain of Milky Way dust and gas, sits one of the most massive galaxy clusters within several 100 million light-years of Earth, the Norma Cluster. It takes its name from the small constellation in whose direction it sits. Norma, the Carpenter's Square, a modest patch of southern sky that contains one of the universe's most dramatic structures. The cluster is located roughly 220 million light-years away, which is close by cosmic standards, and it represents the densest, most concentrated region of the Great Attractor. When infrared and radio surveys finally penetrated the zone of avoidance well enough to study the Norma cluster directly, what scientists found was extraordinary. The cluster contains hundreds of galaxies packed into a volume of space only a few million light-years across. At its heart, two giant elliptical galaxies dominate. Massive ancient systems that have been consuming smaller galaxies for billions of years, growing steadily larger through a process called galactic cannibalism. The hot gas trapped between the cluster's galaxies glows brilliantly in X-ray light, a signature of the enormous gravitational compression happening inside. When X-ray satellites scanned the region, the Norma cluster lit up as one of the brightest X-ray sources on the sky, confirming its immense mass even before its galaxies could be cataloged individually. Surrounding the core of the cluster, galaxy filaments stretch outward in multiple directions like rivers feeding into a lake. These filaments are part of the cosmic web, the large-scale structure of the universe that organizes matter into sheets, walls, and threads separated by vast, empty voids. The Norma cluster sits at one of the intersections of this web, a cosmic crossroads where multiple filaments converge and dump their material. And our galaxy is part of that surrounding material. The Milky Way is not close enough to the Norma cluster to be in any danger of falling in within any time frame that matters for life on Earth. The distances involved are too vast, and dark energy is pushing space apart faster than gravity can draw distant objects together at these scales. But the gravitational influence of the Norma cluster combined with everything else in the Great Attractor region and the Shapley supercluster behind, it has been shaping the path of our galaxy through space for billions of years. Here is something worth sitting with for a moment. The Norma cluster existed before Earth did, before our solar system formed, before a single grain of the dust that would become our planet had condensed from a collapsing gas cloud. The Norma cluster was already ancient, already massive, already pulling on the region of space where Earth would one day appear. In a very real sense, the gravitational environment into which our solar system was born was already shaped by forces that had been operating for billions of years before we arrived. We did not enter a neutral universe. We entered one that already had currents, already had flows, already had a direction built into it. In the last few years, deeper surveys have revealed something humbling. The Norma cluster, impressive as it is, plays a secondary role compared to the far larger structure sitting several 100 million light-years behind it. The real heavyweight was hiding even further away. And when scientists finally mapped its full extent, they had to invent a new category to describe it. Science makes mistakes. That is not a weakness. It is the mechanism. When better data arrives, conclusions change. Estimates get revised. Models that seemed solid get rebuilt from the ground up. This is what separates science from belief. The willingness to be wrong and the tools to discover when you are. The story of the Great Attractor's mass is one of the most striking examples of this process in modern astronomy. When the Seven Samurai published their landmark paper in the late 1980s, their best estimate put the mass of the Great Attractor at roughly equivalent to tens of thousands of galaxies the size of the Milky Way. It was an almost incomprehensible figure, and it dominated the scientific discussion for years. Articles in scientific journals and popular magazines alike described the Great Attractor in terms that made it sound like the gravitational anchor of the entire known universe. Then in 2005, a major X-ray survey called the Clusters in the Zone of Avoidance Project published its findings. The new mass estimate was roughly 1/10 of the original. The team had used X-ray observations to directly measure the hot gas inside galaxy clusters in the Great Attractor region. a more reliable method than inferring mass from galaxy motions alone. Their data pointed to a much smaller total mass than previously assumed. This result caused genuine consternation in the field. If the Great Attractor was only 1/10 as massive as originally thought, it could not be responsible for the full peculiar velocity of our galaxy and its neighbors. Something else had to be supplying the missing gravitational pull. The immediate suspect was the Shapley supercluster several hundred million light-years further in the same direction. Shapley had been known since the early 20th century as an unusually dense concentration of galaxy clusters, but it had been considered too distant to exert significant gravitational influence on our neighborhood. The revised Great Attractor numbers forced a reappraisal. If the nearby source was smaller than thought, the distant source had to be larger than assumed in terms of its influence on us. Detailed modeling of the cosmic flow field incorporating both the Norma cluster region and Shapley showed that the two structures together could account for most of the observed peculiar velocity. Shapley was not a background curiosity. It was one of the primary engines of our motion through space. What the revision really demonstrated was the danger of drawing conclusions from incomplete data. The early mass estimates for the Great Attractor had been calculated from galaxy motions measured over a relatively small volume of space. When the volume of the survey expanded and when direct mass measurements replaced inferred ones, the picture changed substantially. This is actually a source of confidence in the scientific method. Even though it sounds like an embarrassing error, the system worked. New data corrected an old conclusion. The underlying observation that something is pulling our galaxy was always solid. Only the specific attribution needed revision, and the revision opened a door because once scientists accepted that Shapley was a major gravitational driver, they began looking at it much more carefully. And what they found when they mapped Shapley in detail was something that made even the revised Great Attractor numbers look modest. The Great Attractor had led scientists to something even greater. And the deeper they looked into Shapley, the more they realized it was connected to everything around it by a structure so vast and so intricate that it would take a completely new framework just to describe it. Everything we have covered so far has been about pulling. Mass attracts mass. Clusters pull galaxies. Superclusters pull clusters. Everything in our cosmic neighborhood is being drawn in the general direction of the Great Attractor region and the Shapley supercluster behind it. That is the gravitational side of the story. But in 2017, a team of researchers announced a discovery that added a completely different force to the picture. We are also being pushed. The team led by astrophysicist Yehuda Hoffman analyzed a large catalog of galaxy motions and identified something that had been overlooked in previous studies. On the opposite side of our galaxy, from the Shapley supercluster in a region that had attracted little attention precisely because it seemed relatively empty, there was a massive underdensity in the distribution of matter. A void, an enormous one. Voids are not unusual. The cosmic web is made up of dense filaments and clusters separated by vast empty regions. But this particular void was exceptional in its size and in its location, sitting directly opposite from the main gravitational attractors pulling our galaxy forward. Here is the physics that makes this important. In a universe where matter is distributed evenly, each region exerts equal gravitational pull in all directions and things stay put relative to each other. In a universe where matter is clumped, which ours is, the dense regions pull things toward them, and the empty regions exert comparatively less pull. From the perspective of a galaxy sitting near a void, the dense regions on the far side are pulling harder than the void on the near side. The result is a net push away from the void. The dipole repeller, as Hoffman's team named it, is not pushing galaxies away through any exotic force. It is simply an absence of the gravitational pull that would otherwise be balancing our motion in that direction. The void does not attract, so everything near it gets pulled away from it by the stronger gravity on the opposite side. The practical effect is a push. When the team incorporated the dipole repeller into their models of galactic motion, the fit improved dramatically. The motion of our galaxy and its neighbors could now be explained as a combination of being pulled toward Shapley from the front and pushed away from the void from behind. We're being squeezed through space by the geometry of the universe around us. Our galaxy is moving through a corridor of cosmic geometry. Dense structures ahead, emptiness behind. The result is motion that has persisted for billions of years and will continue for billions more. The dipole repeller discovery also had a broader implication. It suggested that our understanding of what drives galactic motion had been incomplete in a fundamental way. Previous models focused almost entirely on identifying the attractors, the dense structures pulling things toward them. The repellers, the voids providing the push from behind, have been largely ignored. Incorporating both sides of the equation produced a more accurate and more surprising picture of the universe's dynamics. And it raised a question that nobody had fully considered before. If voids push and clusters pull, then the large-scale motion of galaxies is shaped by the entire three-dimensional architecture of matter in the universe, including matter we have not yet mapped, including structures at distances our surveys have not yet reached. Which means the forces currently shaping our path through space may extend much farther than we think. Step far enough back from any map of the universe and a pattern emerges. Not chaos, not randomness, a structure. Galaxy clusters sit at the intersections of long, thin filaments of matter. The filaments connect the clusters like threads connecting beads. Between the filaments are enormous empty voids, dark regions that can span hundreds of millions of light years in every direction. Taken together, this arrangement, clusters, filaments, voids, forms what scientists call the cosmic web. It is one of the most dramatic, large-scale structures in nature. And it exists at a scale so vast that individual galaxies are effectively invisible within it. A galaxy inside the cosmic web is like a single water molecule inside an ocean current. The molecule moves. It interacts. But the ocean is what determines where it ends up. The cosmic web was not designed. It grew from the tiny density fluctuations present in the very early universe. Gravity spent billions of years amplifying small differences into the dramatic architecture we see today. Regions slightly denser than average pulled in matter faster. Regions slightly less dense lost material to their neighbors. Over time, the slightly dense became very dense, and the slightly empty became vast voids. Dark matter drove this process faster than ordinary matter ever could have on its own. Because dark matter interacts only through gravity and not through the other forces that slowed down ordinary matter in the hot early universe. It formed the first structures, dense knots and filaments of invisible matter long before the first stars ignited. Ordinary matter then fell into the gravitational wells that dark matter had already prepared. The result, after billions of years of this compounding process, is everything we see today. The cosmic web, the galaxy clusters, the superclusters, the Great Attractor, the Shapley supercluster, and the bulk flow that is carrying our galaxy across space towards structures seeded by quantum randomness more than 13 billion years ago. Here is the staggering implication. The exact path our galaxy is taking through space right now. The specific direction of our peculiar velocity. The particular gravitational basin we are falling into was determined by quantum fluctuations in the first fraction of a second of the universe's existence. Random variations smaller than any particle we can detect, written into space at the moment of creation, grew over billions of years into the mountains of mass that are pulling us across the cosmos today. The Great Attractor is not an accident. It is the inevitable result of a process that began with quantum noise and compounded without interruption for the entire age of the universe. We are falling towards something that started as nothing more than a slight whisper of extra density in the first microsecond of time. And that journey from quantum whisper to cosmic current is perhaps the most extraordinary chain of cause and effect in the known universe. But it also means something profound about our place within it. Because if the seeds of the Great Attractor were random, then so was the direction of our motion. And so was the existence of every structure that makes our journey possible, including Earth itself. Let's be specific about the future. Not vague, not poetic specific. Based on the best current measurements and models, here is the confirmed trajectory of our solar system, our galaxy, and our cosmic neighborhood across the next several billion years. In the relatively near term, over the next few 100 million years, very little changes. Our galaxy continues its orbit around the center of the Milky Way. The solar system continues its journey around the galactic center. Earth continues its path around our star. The pull of the Great Attractor continues, drawing our galaxy incrementally toward the Norma cluster region, though the distance is so vast that no measurable change will occur on any human-relevant timescale. In roughly 2 billion years, our star begins to brighten noticeably as it ages, and its core slowly changes composition. This additional heat will gradually push Earth's surface temperature upward. The oceans will begin to evaporate over geological timescales. By roughly 1 billion years from now, the uncertainty in this estimate is large. Conditions on Earth's surface may become hostile to complex life. In roughly 4 to 5 billion years, the Andromeda Galaxy completes its long approach, and the first close pass between Andromeda and the Milky Way occurs. Tidal forces reshape both galaxies. Star formation surges in the compressed gas clouds. The process of merger begins. Over the following several billion years, the two galaxies complete their merger, settling into a single giant elliptical galaxy. Our solar system may be relocated to a completely different position within the merged galaxy. During this process, though the probability of our star encountering another star closely enough to disrupt our planetary system is extremely low. On longer timescales, the merged galaxy continues to participate in the gravitational dynamics we have been discussing. The local group as a whole keeps falling toward the Great Attractor region, but the expansion of space keeps accelerating, driven by dark energy, making the actual closing of the distance impossible. Eventually, in a very far future, the acceleration of space's expansion will have carried away every galaxy outside the local group beyond the cosmic horizon, the boundary beyond which light can never reach us. The night sky will darken. The universe from our perspective will appear to contain only the merged remnant of the local group galaxies based on measured values of dark energy and the expansion rate. This future is essentially certain as long as dark energy stays constant. If dark energy is changing, if the hints from recent surveys harden into a confirmed discovery, the timeline shifts. A growing dark energy could accelerate the isolation of a local group. A decaying dark energy could slow the expansion and allow more of the universe to remain visible and gravitationally accessible. Either way, the fundamental arc is the same. We are moving through space as part of an enormous gravitational current. That current is real, confirmed, and has been shaping our path for billions of years. The destination we're drifting toward is real. The force preventing us from arriving is also real. And somewhere in the gap between those two forces, the pull and the push, the attractor and the expansion. Earth orbits its star and humanity looks up at the sky and asks where it is going. The answer is both humbling and magnificent. Science moves in waves, long periods of incremental refinement, then sudden leaps driven by new technology. We are currently in one of those leaps. The instruments now operating or recently completed represent a generational advance in our ability to map the universe, measure its expansion, and probe the nature of dark energy. What took decades of work with previous technology can now be accomplished in years. What was previously impossible, mapping millions of galaxies in 3 dimensions across a significant fraction of the observable universe, is now routine. The Dark Energy Spectroscopic Instrument, mounted on a telescope at Kitt Peak National Observatory in Arizona, is the most powerful galaxy mapping machine ever built. It uses 5,000 robotic fiber optic positioners, each one capable of being precisely aimed at a target galaxy, to collect light from 5,000 galaxies simultaneously. In a single night, it gathers data that would have taken previous surveys years to accumulate. In its first 3 years of operation, it mapped over 14 million galaxies and quasars, the brilliantly luminous cores of ancient galaxies powered by supermassive black holes. By measuring the precise distance to each object and the rate at which it is receding, the instrument builds a three-dimensional map of how matter has been distributed throughout cosmic history. Because light takes time to travel, looking at distant galaxies means looking at the past. Galaxies a billion light years away appear as they were a billion years ago. Galaxies 10 billion light years away appear as they were 10 billion years ago. By studying objects at different distances, scientists can watch the universe age in real time, seeing how the distribution of matter changed, how galaxy clusters grew, and how the expansion rate evolved. The data from this instrument is what produced the recent hint that dark energy may be changing. Specifically, the way galaxies cluster together at different epochs of cosmic history does not perfectly match what a constant dark energy would predict. The clustering is slightly different than expected at certain distances, suggesting the expansion rate was not identical at all times. This result caused significant excitement and significant caution in equal measure. The signal is real in the data, but systematic errors, subtle biases in how the instrument works or in how the data is calibrated could in principle mimic the signal. Further verification is needed. Alongside this instrument, a new generation of space telescopes is coming online. These are designed specifically to map the large-scale structure of the universe with unprecedented precision, probing dark energy across even larger volumes of space and at greater distances than ground-based instruments can reach. The Vera-C Rubin Observatory in Chile is conducting a decade-long survey of the southern sky, imaging the entire southern hemisphere every few nights and building the most detailed catalog of transient events, supernovae, variable stars, moving objects ever assembled. The data it produces will revolutionize multiple fields simultaneously. The combination of these instruments operating simultaneously and cross-checking each other's results will likely resolve the Hubble tension within the next decade. It will either confirm the hint of changing dark energy or rule it out definitively. It will extend the maps of peculiar velocity and bulk flow to distances never before reached. And it may reveal new structures, new gravitational influences on our galaxy's path that no one has yet imagined. The next decade of cosmology will likely contain more discoveries about where we are going, and why than the previous century combined. We are mapping our own fate in real time. Everything we have covered so far has been about physics, forces, structures, distances, time scales. But there is a human dimension to this story that deserves its own space. The question of whether the motion of our galaxy through space has any relevance to life on Earth or to the possibility of life elsewhere is not a trivial one, and the answers are more interesting than they might first appear. Start with the most direct connection. The fact that our galaxy is part of a bulk flow toward the Great Attractor means that over cosmic timescales, our solar system will encounter different regions of intergalactic space than it would if the Milky Way were stationary. The density of matter in different parts of the universe varies. The intensity of radiation from distant sources varies. The likelihood of encountering other galaxies and the timing of those encounters is shaped by the bulk flow. These effects are negligible on any human timescale, but they are real. More significant is what the large-scale structure of the universe tells us about the conditions that allowed life to emerge in the first place. Life, as we know it, requires certain conditions. Stable stars that shine steadily for billions of years. Planets with solid surfaces and liquid water. Protection from excessive radiation. Enough heavy elements, carbon, oxygen, iron, phosphorus to build the complex chemistry that life depends on. All of these conditions depend on the history of star formation in our galaxy. And star formation history is directly connected to the large-scale structure we have been discussing. Our galaxy is located in a relatively quiet region of the cosmic web. We sit on a filament feeding into the Virgo cluster, but we are not inside a dense cluster ourselves. Dense galaxy clusters are violent environments. Galaxies inside them are constantly experiencing gravitational disturbances, gas stripping, and collisions that disrupt star formation and scatter planetary systems. Life in the heart of a dense cluster like the Norma cluster would face a far more chaotic and dangerous environment than life in our relatively peaceful cosmic neighborhood. Our location in a mid-density region of the cosmic web gravitationally bound to a small group of galaxies. Moving through space on a smooth and uninterrupted trajectory may be part of what made the emergence of complex life possible here. The conditions required for life are still debated. What we can say is that the location of our solar system within the large-scale structure of the universe reflects the specific history of our galaxy and its surroundings over billions of years. That history was shaped by every gravitational force covered in this video. The Great Attractor shaped the flow of matter in our region. That flow influenced how our galaxy formed and evolved. The galaxy's formation and evolution determined where stars like our star could exist. And our star's existence allowed Earth to form in the conditions necessary for life. Everything is connected, not metaphorically, physically. The pull of an invisible gravitational basin billions of light years away is part of the chain of events that led to every living thing that has ever existed on this planet. That is either terrifying or beautiful, depending on your perspective. Perhaps it is both. And it points toward a final question. The one this entire video has been building toward. Not where are we going, but what does it mean that we are going there at all? We like to think of Earth as the center of something. For most of human history, that was literally what people believed. Earth at the center of the cosmos, everything revolving around us, the arrangement of the universe, reflecting our importance within it. Science has been dismantling that idea for 5 centuries. Copernicus removed Earth from the center of the solar system. Later, astronomers removed the solar system from the center of the galaxy. Then the galaxy was removed from any privileged position in the universe. Everything is expanding away from everything else. There is no center, no edge, no special place. The Great Attractor story adds another layer to this dismantling. Our galaxy is not at rest. It is not drifting randomly. It is being carried by forces that extend hundreds of millions of light years in every direction, flowing in a specific direction toward a specific destination for reasons rooted in quantum events that happened before Earth existed. We are passengers on a galaxy that is itself a passenger in a supercluster that is coming apart at the edges in a universe whose ultimate fate depends on the behavior of a force nobody has ever directly detected. This could feel like insignificance, a vertigo-inducing reminder of how small and contingent everything is. But there is another way to read it. Every force described in this video, the gravitational pull of the Great Attractor, the slow growth of dark matter structure over billions of years, the expansion of space driven by dark energy, is precisely what was required to produce the conditions for complex chemistry, stable stars, and eventually life. The universe did not need to be structured this way. It happened to be because of quantum fluctuations that occurred in the first fraction of a second of existence and compounded over 13 billion years. The specific branch of the cosmic web where our galaxy sits. The specific bulk flow that has shaped our path. The specific neighborhood that provided a calm enough environment for a star like our star to shine steadily for 5 billion years. All of it traces back to conditions that could easily have been different. A slightly different distribution of quantum fluctuations in the early universe would have produced a slightly different cosmic web. A different web would have placed our galaxy in a different region. A different region might have been too violent for stable planetary systems, too radiation intense for complex chemistry, too gravitationally chaotic for the kind of quiet, undisturbed solar orbit that allowed Earth to remain habitable long enough for intelligence to emerge. We are not at the center of the universe. We are at a very specific, improbably favorable address within it, reached by an extraordinary chain of events spanning the entire age of the cosmos. The Great Attractor is pulling us toward a destination we will never reach. The expansion of space is carrying away everything beyond our gravitational reach. The The universe is becoming darker and lonelier with every passing billion years. And in the middle of all of this vast, indifferent, magnificent machinery of gravity and expansion and quantum chance, a species on a small planet around an ordinary star found a way to measure it all, to map the forces acting on their own galaxy, to calculate the mass of things they cannot see, to name a gravitational basin they will never visit. That is worth pausing on. The universe is pulling us forward, and we are the part of the universe that turn around to look. That is the full story of where Earth is going and why. From quantum fluctuations to superclusters, from a force we could not see to a map of our own cosmic fate. If this left you with more questions than answers, that is exactly where science lives. If you found this worth your time, leave a like. It helps more people find their way to these ideas. Subscribe if you want to keep going deeper. There is always something stranger waiting one layer further out.